Hey guys, I was just talking with my friend Jamie about how it feels like I'm learning a foreign language in my chemistry class. It's crazy to think that element symbols can translate into words, and that words can be used to represent elements. Last time, we learned about how to write simple ionic compounds. But on the back of my sports drink bottle, I saw the words potassium phosphate. What's that? Jamie is extremely smart. She told me that those words represent a chemical formula. Chemical formulas are simply symbols that explain how many and what kind of atom make up a compound. Chemical formulas can be written for ionic and covalent compounds. Let's just look at ionic compounds for now. Remember, all elements just want to be like noble gases. They have 8 outer electrons. This is called the octet rule. Ionic bonds happen when there's a transfer of electrons. Before we can write the chemical formulas for ionic compounds, let's get a few things straight. To sort out all this ion information, let's make a table. Write the group number across the top. Then, down the side, let's look at whether an atom will lose or gain a valence electron, how many will be lost or gained, and the charge of the ion formed. Remember, groups 1, 2, and 13 are metals. It's easier and requires less energy for those elements to lose electrons and make cations. Elements in groups 15, 16, and 17 are nonmetals and tend to gain the few electrons needed to reach a full octet. Elements in group 18 are too cool for school and won't react. When ionic bonds form, atoms are going to lose or gain just enough electrons to get their happy number 8. Okay, well, what about group 14? They look a little strange. They have 4 valence electrons, so they can lose electrons or they can gain them. Look at groups 1, 2, and 13. These atoms have 1, 2, or 3 VEs. It is easier for these elements to lose 1, 2, or 3 electrons instead of trying to gain 7, 6, or 5 to get 8. Jamie explained to me that trying to win this battle would be like trying to take your iPhone back from your baby sister after she took it from you. Sometimes it's easier to just give in and let her take it. When these atoms lose electrons, the charges become +1, +2, and +3. Most of the time, elements in group 14 form covalent bonds since they are halfway to that happy number 8. It is easiest for them to share electrons with another element. Look at groups 15, 16, and 17. These atoms have 5, 6, and 7 VEs and are more than halfway to get that cool super 8. It just makes more sense for these elements to gain electrons rather than to lose them. They're almost there. It's like you're running a race and you can see the finish line. You're almost there and all you need is just a little bit of energy to get all the way. I mean, you've come this far and there's no turning back now. When these atoms gain electrons, the charges become -1, -2, and -3. Now we're ready to write the chemical formulas for ionic compounds. Let's see what happens when sodium and phosphorus bond. A new compound called sodium phosphide will form. Sodium is in group 1, so according to our chart we made, sodium will lose 1 electron. Phosphorus is in group 15, so it will gain 3 electrons. But sodium only has 1 electron to give. Let's take a look at the ions and see if we can't figure a few things out. To write the ions, the charges are written to the right of the element, but a little bit higher, like an apostrophe. The opposite charges on these ions hold the compound together. When the ions combine, the net charge must be 0. Ionic compounds are electrically neutral. So far, we have 1 positive charge from the sodium ion. and 3 negative charges from the phosphide ion. So our overall charge is -2, not 0. It looks like we're going to need some more positive charges in order to get a neutral compound. 2 to be exact. It looks like 2 more +1 sodium ions will do the trick. 3 sodium ions and 1 phosphide ion is needed to have a neutral compound. We write chemical formulas using little numbers called subscripts. Subscripts tell us how many of each type of atom are present. That little 3 only applies to the sodium atom. Cations are always listed first in the chemical formula. So that is how you write the chemical formula for sodium phosphide. But what about that potassium phosphate I saw on my Gatorade label? My girl Jamie told me that phosphates are not the same as phosphides. A phosphate is an example of a polyatomic ion. This is an ion made of more than one atom. When writing the chemical formulas containing polyatomic ions, the net charge still has to equal 0. We have 3 negative charges and 1 positive charge so far. That means, again, we're going to need another 2 positive charges in order to get a neutral compound. Okay, so we need 3 potassium ions, each with a positive charge, and 1 phosphate ion with a -3 charge, in order for the compound to be neutral. The new chemical formula looks like this. So even though they're polyatomic ions, there's nothing to be afraid of. The same rules apply. Okay, that is a lot of information. And I'm not going to lie, sometimes I can get a bit lazy. I just wish there was a way that would help me figure out these chemical formulas. Well, my friend Jamie says I'm in luck because it's called the crisscross method. Let's look at another example and apply the crisscross method. Aluminum and sulfur, when combined, will form aluminum sulfide. Aluminum is in group 13. It's a metal, and it will be the cation in our ionic compound. Sulfur is in group 16. It's a nonmetal. Sulfur will gain electrons, and aluminum will lose electrons. Write the ions. Now, write the symbol of the element under the ions, like this. Now, let's crisscross the numbers. Draw an arrow from the cation to the sulfur, and from the anion to the aluminum. Next, bring down the numbers only, not the charges, and write them as subscripts. Well, Jamie has been a huge help to me, and I hope it's helped y'all too. I'm just starting to understand this whole chemistry language. That's it for now, guys.